Hello everyone, this is the video for chapter 10, lesson 2. So in our last lesson, we talked about graphing radical equations or square root equations. Today we're going to take a break from graphing. We're going to take a deep dive in working with radicals. So it could be multiplying radicals, it could be simplifying radicals, all kinds of things. But our whole focus is just looking at when we're working with radicals. So here's some basics here. When we have a square root of a times b, we can look at that as a square root of a times a square root of b. So for example, if we have a square root of 4 times square root of 9, you can multiply what's inside and say, okay, 4 times 9 is square root of 36, or simplify square root of 36 and make that 6. Another option is to look at this as square root of 4 times square root of 6, and then reduce, simplify each individual square root. And so the square root of 4 is 2. Sorry, there is a typo here. This should be a 9. And the square root of 9 is 3. And when you multiply those, you get 6. Okay? So let's talk about simplifying square roots. When we simplify, we're going to use what we call the factor tree, which hopefully by now you're kind of familiar with. But the factor tree, we are going to basically break down the 12 into its products, which would be like 4 and 3. And mind you that when you're breaking down the square root of 12, really what this is saying is square root of 4 times square root of 3 makes 12. And we can break down square root of 4 into 2 times 2, right? 4 is broken down to 2 times 2. So basically what you have is square root of 2 times square root of 2 times square root of 3. So these are, I'm going to highlight them, these are the factors of square root of 12. Now, one really interesting thing, if you plug this on your calculator, square root of 2 times square root of 2 actually makes 2. And what you'll notice is a square root of itself times square root of itself. So like whatever, if it has the same radicand inside the square root, those, when you multiply the 2, the square root cancels basically, and then what you have is 2. Or you can even think square root of 4 is just 2. So that even makes sense here. Now, for the sake of convenience, I'm going to stop. I'm not going to put the radical sign around every single thing that I factor, because if I can understand in my head everything is a radical, you can just do the factor tree and factor it out. So basically, what you have here is, if I bring this down, what I have is square root of 2 times square root of 2 times square root of 3. Times square root of 3. But square root of 2 times square root of 2 is just 2. So this basically reduces down to 2 times square root of 3. And that is the reduced version of square root of 12. If you plug this in the calculator, you would get the same decimal as if you plugged in square root of 12 and entered. You would get the same decimal answer. So let's take a look at B. 56, I'm going to break that up into 6 times 9. Mentally, you might be thinking, okay, there are square roots around everything. So like 9 would break down to 3 times 3. And then 6 would be broken down to 2 times 3. Well, everything in here is a radical. So when you have pairs, radical of 3 times radical of 3, that is a positive 3, or a positive whole number of 3. There's no more radical sign. Then I basically have square root of 2 times square root of 3. Those do not break down, and I can't pair anything up. So when I bring them together, that's square root of 6. Okay, 180, I could break that down to 18 and 10. 10 breaks down to 2 and 5. 18 breaks down to 2 and 9. 9 breaks down to 3 and 3. Okay, 3 and 3 is a pair, and guess what? This 2 and this 2 is also a pair. So what I have now is 2 times 3 times radical of 5. And if I simplify even more, that's 2 times 3 is 6. So I have 6 times the radical of 5. All right, what do we do when we have square roots that are being multiplied? So there are two ways you can go about this. One way, like we looked at above, is you can multiply what's in the radicals are, look at it as a big number and then reduce, or you can actually reduce each individual term. So I'll do this first one two ways. Radical of 5 does not break down to anything smaller, but 10 does. This would be 2 and 5. And so really I have radical of 2 times radical of 5 times radical of 5. Don't forget about that 5. So radical of 5 times radical of 5 is 5. Radical of 2 does not pair up with anything, so it's 5 times radical of 2. Another way you could look at this is multiply and make this square root of 50, and then break that down. And when you break it down, maybe you would have like 25 and 2, right? 25 times 2 is 50. Well, radical of 25, basically that breaks down to 5 and 5, right? 25 breaks down to 5 and 5. So what you have is a pair of 5, which means that's 5, and you're left with this radical of 2. So 5 times radical of 2. The answers are the same. You're just going about different ways, and it's up to you on how you want to do that. Both are fine. I prefer breaking down the numbers so I have smaller numbers to work with. So I'm basically looking at these square root of 6 and square root of 8 as two separate factor trees that I'm going to do. 6 breaks down to 2 and 3. 8 breaks down to 2 times 4, which breaks down to 2 and 2. So I'm looking for pairs. Here's a pair of 2. Here's a pair of 2. And so what I have is 2 times 2 times square root of 3. 2 times 2 is 4, so my answer is 4 times square root of 3. What do we do when we have a square root with variables? Okay, so again, you can break these up into each individual square root. So what I have is like square root of 32 times x to the second power, square rooted, times square root of y to the fourth power, times square root of z to the fifth power. So we're going to go back to this idea of square roots, I guess, of a power. Basically, when you're square rooting a power, you're just dividing that by 2, because a square root is, what is that? The same thing multiplied by itself to produce the radicand. So essentially, I'm really dividing all these powers by 2. So we'll take it baby steps. Let's do the 32 first. Let's break this down. 32 would be 4 and 8. 4 would be broken down to 2 times 2, and then 8 would be 2 times 4. 4 breaks down to 2 times 2 some more. So I have a pair of 2's here and a pair of 2's here. And then I have 2 times 4. Sorry, the 4 is not in. I have 2 left over, right? So this 2 is left over. So I have basically 4, right? 2 times 2 times a radical of 2 is broken down from the 32. Let's talk about the radical of x squared. Well, x squared divided by 2, the power divided by 2 is just x to the first power. Y to the fourth power divided by 2 is, I guess the power divided by 2 is y to the second power, okay? And because these are divided evenly, the square root is gone. Now, z to the fifth power is a different story because I have a odd number, and when I divide that by 2, it doesn't go out evenly. It's like, what, 2.5, right? So you can look at it like this: z to the fourth power times z to the fifth power, all under the radical sign. Well, if you think about this, if I just break down the z to the fourth power itself, that would be z to the second power. Now, z to the first power, when you divide it by 2, like, it doesn't come out evenly. So we're going to leave this as a radical. This is going to be z to the first power, but I don't have to put that 1 there. Okay, so then now let's reorganize this and bring it together. Now, all of these, 4, x to the first power, y to the second power, z to the second power are going to go in front because they are not in a radical sign. So basically we're going to have 4x y to the second z to the second. And then we're going to bring everything that has a radical under the same roof. So 2 and z, I'm going to bring together as under the same radical sign. So essentially this is my answer. Now there's one more thing to take note of, and that is if you have a power to an odd number, so I'm going to put this one in pink because it's x to the first power. And this is just kind of one of those things. If you have a power to an odd number, you need to put that absolute value. So I'm going to put that, make a note here. I would write that down if I were you. So if you have odd exponents that are simplified, they're not in a, you've simplified them from a root. Odd exponents need to be in absolute value. And that's because we want to keep it positive. So this x to the first power, I would want to put an absolute value around it. So in my answer, I'm going to put an absolute value around it. This is my final answer. So it's nothing crazy. You just have to remember, if you have a power that's not in a radical, you've simplified it from a radical, you've broken it down, and it's odd, you need to put that in an absolute value. So B, let's try this out. You could pause it and try it out on your own if you'd like, but I'm going to put everything, I'm going to separate everything out. I think it kind of helps me identify what's going on. And then I can just look at each individual term by itself and not worry about too much clutter. So 56, I'm going to do the factor tree, 7 and 8. 8 breaks down to 2 and 4, which breaks down to 2 and 2. So I have 7 and 2, and then 2 and 2. And here's my pair. So I'm going to bring the 2 out, and then I'm going to bring a square root of 17 out because 2 times 7 is square root of 14. Did I say 17? Square root of 14. That's what I meant to say. Maybe I'll highlight kind of what's the simplified ones. Okay, x square rooted, square root of x. I can't reduce that or change that, so that's going to stay as radical. Y to the 10th power square rooted. Remember, we're just dividing the power by 2, so it's y to the 5th power. Z to the 5th power, remember, we're going to look at this as z to the 4th times z. And so really I have z to the 2nd and a radical of z, okay? So I'm going to highlight everything that's been reduced or simplified, I guess, that and that. Now I'm going to bring this all together. What I would have is 2 times square root of 14 times square root of x times y to the 15th times z to the 2nd times square root of z. Now let's reorganize. Everything that has a radical is going to go under the same roof. Everything that does not have a radical, we're going to put, I don't know why I wrote that as 15. That should be y to the 5th power. Put in front. Now, if there's an odd exponent, which is right here, we need to put that in a radical or an absolute value. So it's going to be 2 times absolute value of y to the 5th times z to the 2nd, and then everything under the same roof. 14 times x times z. That's a z. Okay, hopefully that makes sense. That is our final answer. Let's talk about when there is a quotient, so like a fraction with a radical, okay? When you have a radical over an entire fraction, like a radical of a over b, you can look at them as being separated as a radical of a over a radical of b. So when we're looking at this, radical of x to the 3rd over y, You can look at it as a radical of x to the third times a radical of 9. Now, radical of 9 or square root of 9 makes 3. So 3 is the most simplified version of square root of 9. And then, like we said, when there is an odd, we kind of have to look at this as what, x to the second times x to the first. And x to the second reduces down to just x times x to the first, or just x, square rooted of x. If this is the first, if this is reduced and an odd number, we need to put that in a absolute value. So that's where this answer is coming from here. Now, if you have a denominator that is a denominator that is a square root, so like I say, I have a square root of b over a square root of b. The problem is it's mathematically impossible and unavailable to have a radical in your denominator. So the way we're going to combat that is by basically multiplying by that denominator, as writing it as like a version of itself over itself. Okay, so square root of b over square root of b. What this is basically just another version of 1. Just like if I put 2 over 2, that equals 1. If I put 4 over 4, that equals 1. If I put 3.5 over 3.5, that equals 1. So anything over itself, we know, is 1. And so we're using this idea, this mentality of multiplying by 1 to say, I'm not changing the value of what I'm seeing. I'm just manipulating and reorganizing my information so that what will happen is you have square root of b times square root of b, and this will become b without the radicals. So the radicals will cancel. Let me try this with numbers just so we're not like confused by what's going on. Sometimes when you see numbers, it helps you out a little bit. So let's say I have 2 over a radical of 3. This radical on the bottom is unacceptable. So I'm going to multiply this by radical of 3 over radical of 3. This is just another version of saying 1. So when I multiply, this will become 2 times square root of 3 over 3. And you can have a radical on top, that's fine. You just cannot have a radical in the denominator. If you have a radical in the denominator, you've got to figure out a way to cancel it. So looking at this example here, simplifying expressions with quotient properties. So we've got odd powers. To me, I would write this as a to the 8th power times a to the 1st over b to the 4th power times b to the 1st, so that I can simplify. And when I simplify, a to the 8th square rooted is a to the 4th. I'm dividing the power by 2 times a square root of a. Then below I have b to the 2nd power times a square root of b. Now, what is the thing that we have to get rid of here in the denominator? It is the square root of b on the bottom. So I'm going to multiply by square root of b over square root of b. When I multiply this, what's going to happen is I have a to the 4th times square root of a times square root of b. So I'm just going to put them under the same roof. And then I have b to the 2nd times b. Well, that's basically my answer, but I'm just going to bring this b to the 2nd times b together, because b to the 2nd times b will be b to the 3rd. And so I can rewrite that as just b to the 3rd on the bottom. And that's my answer. Let's look at this one. We can look at this as square root of 6 over square root of 12 times square root of y over 1. We look at this, this is actually something we can reduce. That would be 1/2, right? Now that's all under a square root still, and the y is still in the numerator. So we have 1y over square root of 2, which really means I have square root of y over square root of 2. So what we see here is a radical in the denominator. I'm going to multiply by radical of 2 over radical of 2. And this will become radical of 2 times y over 2. That's my final answer. All right, let's talk about multiplying radicals. Like, I want to multiply everything here. Well, really, I can just multiply my whole numbers together. I can multiply any like term that's in a radical together and bring them together under the radical. So 6 times 4 is 24. Everything else is in a radical, so 8 times 2 is 16. C to the third power times C to the first power is C to the fourth power. D to the fifth times D to the third is D to the eighth. So we're going to simplify and reduce what we have here. This would be 24 times square root of 16 is 4. Square root of C to the fourth is C to the second. Square root of D to the eighth is D to the fourth. So actually all my radicals go away completely. Now I just need to bring together 24 times 4, which is 96, and then bring everything else down. So this was nice because it got rid of all the radical signs. All right, our last problem. We need to conjugate to rationalize a denominator. So we have a problem here. Our denominator has a square root of 2 minus 3. Now, this is not as simple because I can't just multiply like square root of 2 minus 3 over square root of 2 minus 3. This idea here comes from, you've got basically like an A and B term. So A minus B, if you multiply the same exact thing, A minus B, it's actually not going to cancel things out. You're going to have more created when you multiply it than what you started out with. So we're going to do what we call the conjugate. The conjugate of A minus B is A plus B. And this is where when you cross, when you cross multiply or when you multiply like this, what happens is the middle term cancels. And this is back to chapter 7 and chapter 8. Middle term cancels. And what you see is that you're just squaring the first and second term. What you have is A squared minus B squared. So we're going to utilize this idea. Instead of just multiplying the same thing top and bottom, square root of 2 minus 3, we're actually going to multiply the conjugate, which is square root of 2 plus 3 on the top and bottom. What that's going to do is it's going to help me cancel some of this stuff out, especially my square roots. So when I multiply this, what I will have is square root of 2 times parentheses square root of 2 plus 3, because it's multiplying everything, over square root of 2 squared minus 3 squared. And now I can work this out. So if I distribute this, what I have is square root of 2 times square root of 2, which is just 2. And then I have square root of 2 times 3. So it's square root of 2 times 3. I'm going to put the 3 in front, actually. So I have square root of 2 times 3. But we like to put our whole numbers in the front. Then on the bottom, I have square root of 2 squared, which cancels out the square root. I have 2 minus 3 to the second power, which is 9. I'm going to bring this down. And now what I have, the top I think can stay as is. There's nothing I really need to do to change it. 2 plus 3 times square root of 2 over 2 minus 9 is negative 7. This is my final answer. And I know it looks funny because you've got a negative on the bottom, but that's what it is reduced. So I know this idea is tricky. We'll do a few more examples in the future, but it's called a conjugate. You're multiplying by the opposite. The a minus b times b, a plus b. We'll cancel out the middle term. Remember this from chapter, I think it was like 8, where you're just going to square both a and b terms and keep it as a subtraction sign. All right, that is all I have for you today. So there are a lot of components here. It just takes a lot of practice, a lot to keep track of, but hopefully as you keep going, it's going to kind of fall into place.